Test 4 is it's going to cover sections 3.2, 3.3, 3.4, 3.7, 3.8, and 3.9. A lot of chapter 3. Of course, 3.2 there, that's the mean value theorem. And also the other theorem, forget the name right at the moment. The other theorem is Rowe's theorem. Yeah, so definitely be familiar with those two theorems. Be able to work with those theorems, especially conclusion. Be aware of those conclusions there. Yeah, now 3.3 was the section there we talked about what the derivative means as far as the graph is concerned. The first derivative, well, that can tell me two things, increasing and decreasing, and also kind of connected with that is the local maxes and mins. Yeah. If you do a little sign chart, you can get all that information right off of the first derivative. The endpoints of those, of course, are the critical numbers. Derivative equals 0, derivative does not exist. So get a lot of information out of the first derivative. The second derivative, as far as the graph is concerned, tells me about concavity, concave up or concave down. Yeah, the critical numbers give you the endpoints of those, and then do a little sign chart and check. If the second derivative is positive, it's concave up, and negative, it's concave down. And anywhere you have a change in concavity, you also get those inflection points. So yeah, I'll probably have a couple where you have to do those little sign charts for the first and the second derivative to determine those things. Now, the other thing we talked about on those was our second derivative test. For maxes and mins. And it was kind of a combination, right, of the first and the second derivative. You still use your first derivative equals 0 on this second derivative test, but then those critical numbers where the derivative equals 0, if you plug them into the second derivative, that can determine also your local maximum, because yeah, if you've got concave up at a derivative equals 0, you know that you've got a min there, because it's concave up, the derivative equals 0, so we know we're at a horizontal tangent. Yeah, so it's got to be a local min there, and vice versa. But yeah, we'll have you do the second derivative test to find local maxes and mins as well. All right, 3.4 was your limits at infinity. Remember, that was where we did our divide by the largest power of the denominator. And you can find the limits at infinity as opposed, if we're looking at a limit as x goes to 2, what we're looking to do there is various things, factor and so forth and so on. But as far as limits at infinity, the really nice little technique is, divide top and bottom by your largest power of x, and you can get such as this. If we divide by the largest power of x, it sets it up nicely where we can tell what's going on there. So we've got several examples there. There's several things that can happen, but that's the basic idea. So probably a couple of those types of problems other things associated with that. Let's see, 3.7, I believe 3.7 was our optimization problems. And so on those, what I would say there, I'm not going to go through those all again, but what I would say is I would probably suspect at least one of each kind. We know we had the distance, maximizing or minimizing the distance ones. Probably one of those. Another one we had where the fencing, either minimizing the fencing or maximizing the area that you could cover in a scenario with certain fencing. Probably one of those. And what else we had? We had like a volume, maximizing a volume or minimizing the surface area. Yeah, so probably would suspect one of each of those. 3.8 was Newton's method. Then your formula there definitely would know the formula. X sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. That's the formula for Newton's method. It just allows you to find roots of an equation. So I'd be familiar with that, know how that works and all that good stuff. And last but not least, 3.9 was the antiderivatives. And that's, one of the things on this test is, and I guess from here on out in calculus, however far in calculus you take it, you got to remember, is it an antiderivative or is it derivative? Because, of course, the antiderivative is exactly the opposite process. But be aware, because on optimization problems we're using the derivative, mins and maxes we're using the derivative, but I will have a couple of problems where you have to find the antiderivative. Like I said, it's the opposite process, but just be watching out for that. Anything else? That's a pretty quick rundown of what we've done, but pretty good material for a test there.